Hi, my name is Dr. Tishan, and I'd like to show you an example of how to solve a rational inequality. This is what an example of a rational inequality looks like. Let's look at the three-step process that we want to go through in solving a rational inequality first before we do this example. First, when you're solving a rational inequality, you want to write your inequality in the correct form. The left-hand side, you need a single fraction with a polynomial over a polynomial. Then you want your inequality sign, and then you want a 0 on the right-hand side. This is the proper form for the setup for a rational inequality. Once you have your inequality in the correct form, then step 2, you want to find the zeros of the polynomial numerator and denominator. Find the zeros of the numerator and the zeros of the denominator and plot them on a number line. And then finally, you want to test each of the intervals broken off by the zeros on your number line to see where the true and false regions are, and then finally state your solution when you're done. So let's go ahead and put these steps into practice with this example. This example we're going to do together here is 3x minus 5 over x plus 2 is less than or equal to 2. So this is the example we'll do. So first, we want to write the rational expression in the correct form. And as you notice, you have a 2 on the right-hand side. Our right-hand side needs to be a 0. So we need to have a 0 on the right-hand side, not the 2. We need to begin by moving the 2 over to the left-hand side. So we're going to subtract 2 from both sides of this inequality. So you have 3x minus 5. We'll just keep the fraction together here over x plus 2. Here's your left-hand side. But we want to subtract 2 from both sides. You want to subtract 2 less than or equal to, and when you subtract 2 from 2, you get a 0. Subtract 2 from both sides of the inequality. I want to do that first. Next, now we have a 0 on the right-hand side. Left-hand side has to be a single fraction. Polynomial over polynomial has to be a single term. We have 2 terms here. We have to write it as a single term. So we're going to need to get a common denominator. Let's get a common denominator. We have a fraction form here, but this 2, if we want to put it over 1, to get a common denominator, we're going to have to take a look at these 2 fractions and determine what the common denominator should be. In this case, the common denominator needs to be x plus 2. Okay, so we're going to write this inequality. We're going to put x plus 2 for our common denominator for this fraction, x plus 2. All right, and so now we have to adjust the numerators. First numerator, well, we have the x plus 2 in the denominator, so we could just take the numerator, 3x minus 5, and just bring it down. All right, your second fraction, all right, we need an x plus 2. We need the denominator to be x plus 2. All right, so whatever we need in the denominator, we need that. So we're going to have to take what we're multiplying denominator by to keep everything balanced here. We're going to have to multiply the numerator by the same thing. We want to multiply the numerator by x plus 2 as well. Okay, so our new fraction here, you've got the 2 out front, but we have to multiply it by the x plus 2. So here we achieve a common denominator. Right. Next, what we want to do is we want to write these 2 fractions as one fraction. So we're going to combine. We're going to keep the denominator. We're going to keep the denominator, and we're going to combine the numerators, okay? So we have 3x minus 5, and we need to distribute here, and be careful with the subtraction out front, okay? Because the subtraction out front, you can put the subtraction with the 2. Be careful when we distribute the negative 2 in here. So it's going to give us a minus 2x, all right? And then distribute the negative with the 2. Negative 2 times 2 gives us a minus 4. All right, so here we have our common denominator. We combine the numerators, and as you can see, we can still collect like terms in the numerator. So let's go ahead and do that. So we have the x plus 2 in the denominator. All right, in our new numerator, collect like terms. We've got 3 x's and take 2 x's away, so that leaves us an x. All right, and then a negative 5 and a negative 4 is a negative 9. So here we have our rational inequality set up, and it is now in the correct form. Left-hand side, we have a single fraction with a polynomial over polynomial, and then you have your inequality sign, and then we have the 0 on the right-hand side. So step 1, we want to make sure we have our our rational inequality in its correct form. We've achieved step 1. We need to now move on to step 2. Step 2, we want to find the zeros of the numerator and denominator. We need the zeros of the numerator and denominator, and we're going to plot those zeros on a number line. So we're going to draw a number line here first. Okay, so draw a number line. Number line is going to span from negative infinity to positive infinity. Okay, so we can't see those, it just goes infinitely long. So this is our number line. Our numerator, let's go ahead and find the zeros. Our numerator, x minus 9 is equal to 0. I'm going to just do some mental math here. X minus 9 equals 0, add 9 to both sides when x is 9. So positive 9 would be one of our zeros to place on the number line. And then x plus 2 is equal to 0. Subtract 2 from both sides. X equals negative 2 would be our other 0. So our 0 of the numerator is 9. Okay, our 0 of the denominator is a negative 2. Now the denominator of our fraction, okay, because we have to be careful with this inequality sign, denominator can never equal to 0. It can't have 0 in the denominator of a fraction because it's undefined. So when we're looking here, we determine where the zeros are. Because of the inclusiveness, okay, numerator is 0, we would be able to include that numerator equal to 0 in our final answer, but denominator can never be 0. So the negative 2 with the denominator 0, we want to be careful with that. We probably want to put an open circle or something there, just put a mark there so you know that once you do get to the final answer, that you cannot include the negative 2 in your final answer, okay? And then what we do is we're going to, step 3, we're going to go ahead and take each of these intervals. We have 3 intervals now. We have negative infinity to negative 2, negative 2 to 9, and 9 to infinity. And we're going to pick a test value in each of the 3 intervals, and we're going to test them in our inequality to determine if it works, if it gives us a true statement or a false statement. So when you're solving these inequalities, we're going to have infinitely many solutions, and our solutions are contained to intervals. We just have to determine now which intervals our solutions lie in. So let's start in our first interval here, negative infinity to negative 2, and let's pick a test value in this interval. All right, you can test any number that you want between negative infinity to negative 2. I'm going to test negative 3. Any number that you test will be representative of the entire interval. So test x equals negative 3. When you plug negative 3 minus 9 is a negative 12. Negative 3 plus 2 is a negative 1. Negative 12 divided by negative 1 is 12. Is 12 less than 0? That is not true. Okay, so now I'm going to write false. That's a false. That gives us a false inequality statement. False statement means the solutions do not lie there. So now let's go in to check our next interval. Our next interval spans from negative 2 to 9. We want to pick a value to test. We want a test value in this interval. You can pick any number in the interval you'd like. Because 0 is in there, I like to pick 0 if it's in the interval that I'm testing. So you take 0, plug it in, 0 minus 9, that gives us negative 9 over 0 plus 2 is 2. So negative 9 divided by 2, negative 9 halves. Is negative 9 halves less than or equal to 0? It is. This is true. This gave me a true inequality. So my solutions, this is a region where all these infinitely many numbers between negative 2 and 9 will fit in my solution. I still have to check my third interval. So third interval, I need to pick a number between 9 and infinity, and any number you would like to use in this interval would work. I'm going to pick 10. 10 is in here. All right, 10 minus 9 is 1. 10 plus 2 is 12. 1, 12. Positive 1, 12. Is that less than 0? It is not, so this gives us a false inequality statement also. So here we have, this is the work we're doing to see where the solution lies, and here we have a picture of where the solution lies. We want the solutions between negative 2 and 9. All the infinitely many solutions between negative 2 and 9 work. Now we have to just take a look at the endpoints here, okay? We are including it's less than or equal to, so because the numerator is all set, when x equals 9, we do have 0 equals 0, and that is okay, so we can include, so you put a bracket, closed circle back in the days when I was growing up, but we put a bracket to include it facing the interval, but we do not want to include the negative 2. I know it looks like it's inclusive for this symbol here, but we do not want to include the negative 2 in our interval, because if we include the negative 2, it puts a 0 in the denominator, we would have an undefined fraction, which does not make it a true statement. So you do not want to include the negative 2. So parenthesis over here. So this is where the solution lies, okay? and we want to go ahead and we need to state our solution. We're going to write proper notation to state our solution, but once the work is done for the problem on the number line, stating your solution is just, looking and just writing this. Okay, so the solution for this problem, the solution for this inequality right here, for this rational inequality right here is going to be, we want all the numbers that are greater than -2, but not including -2, okay? All right, but up to 9, but we will include the 9, so bracket after the 9, and here's the solution to our example, example number 1. I hope that helped. Thank you for watching. See you next time.